Hello and welcome to the last section of Unit 2, the last chapter of Unit 2, The Sun, Our Extraordinary Ordinary Star. Here are the vital statistics for the Sun, just as we had vital statistics for all of the planets in the solar system. We also have vital statistics for the Sun in our solar system. You can look over these at your leisure, but we are going to go over most of the interesting science behind them rather than just going over kind of the statistics as we did with the planets. The Sun appears to have a surface only because most of its visible light comes from one specific layer. This region, which is about 400 kilometers thick, is appropriately called the photosphere or the sphere of light. The density of the photosphere's gas is low by Earth standards, about 0.01% as thick as the air we breathe. The photosphere has a blackbody radiation that corresponds to an average temperature of 5,800 Kelvin. As you can see in photos of the Sun, if not so much by staring directly at it, which you shouldn't do, the photosphere appears darkest towards the edge or limb of the solar disk, a phenomenon called limb darkening that occurs because we see regions of different temperatures at different depths in the photosphere. Wherever we look at the Sun, we see the light is roughly equal to amounts of the Sun's atmosphere. Because the Sun is spherical, the light we see leaving the Sun at different places actually comes from different levels of the photosphere. Looking at the center of the Sun's disk from Earth, we see farther into the Sun's atmosphere than when we look towards the limb. The photosphere is hottest and brightest at its base, and so because it is a black body, the center of the Sun's disk, where we see deepest into it, looks brighter and yellower than it does at its limb. Under good observing conditions and using a telescope with special dark filters for protection, you can see a blotchy pattern called granulation on the photosphere. The bright granules typically measure about 1,000 kilometers across and are surrounded by relatively dark boundaries. Time-lapse photography shows that granules form, disappear, and then reform in cycles that last about 20 minutes. At any given moment, the several million granules cover the solar surface. Immediately above the photosphere is a dim layer of less dense stellar glass called the chromosphere, or sphere of color. This unfortunate name suggests that it is the visible layer the layer we normally see, but for centuries the chromosphere was visible only when the photosphere was blocked during a total solar eclipse. During an eclipse, the chromosphere is visible as a pinkish strip some 2,000 kilometers thick around the edge of the dark moon. Today, astronomers can also study this chromosphere through filters that pass light with specific wavelengths strongly emitted by it, but not by the photosphere, or through telescopes sensitive to non-visible wavelengths that the chromosphere emits intensely. High-resolution images of the chromosphere reveal numerous spikes, which are jets of gas called spicules. Spicules occur when hot gas is in and below the photosphere gets trapped by the Sun's magnetic field. Most of the solar gas is so hot that it is ionized, a phenomenon called plasma. However, some of the gas trapped by the magnetic field is electrically neutral. The neutral gas acts like a bubble in water. Namely, it pulls the magnetic field, trapping it and the plasma surrounded it upward, creating a spicule. The magnetic field is then forced open and all of the trapped gas escapes, then collapses and fades away. A typical spicule rises for several minutes at the rate of 72,000 kilometers per hour to a height of nearly 10,000 kilometers. At any given time, roughly a third of a million spicules cover a few percent of the Sun's chromosphere. Spicules are generally located at the boundaries of enormous regions of rising and falling chromospheric gas called supergranules. Like granules, supergranules are regions of convection on the Sun, but on a much larger scale. And supergranules are typically across more than twice of Earth's diameter. They typically contain about 900 granules, and they typically last between 1 and 2 days. The details of their formation is still under investigation. So we can see here, these are the spicules that are jetting up, and this is the diagram showing the process that we were talking about earlier. The solar corona is an outer layer of the sun where the temperature goes from about 10 to the fourth in the chronosphere over the course of a transition zone, which isn't that thick, to about 10 to the sixth or 1 million Kelvin at the side of the corona. This unexpected increase in temperature was discovered around 1940 as a result of the high temperature's effect on the spectrum of the sun's corona. The hotter a gas is, the more of it is ionized, more electrons are stripped off each atom. Astronomers discovered that the corona contains the emission line of several highly ionized, therefore very hot elements. For example, a prominent green line caused by the presence of iron-14, an iron atom stripped of 13 electrons, appears in the coronal spectrum. It is now known that coronal temperatures are typically in the range of 1 million to 2 million Kelvin, although some regions are even hotter. Although its temperature is extremely high, the density of gas in the corona is very low, about 10 trillion times less dense than the air at the sea level on Earth. The low density partly accounts for the dimness of the corona, which otherwise would outshine the photosphere. Astronomers have observations indicating that the sun's complex magnetic fields provide mechanisms for lifting gases into the corona and heating them to the extreme temperatures observed there. The details of these processes are a very active area of research today. Just as Earth's gravity prevents most of our atmosphere from escaping into space, so too does the sun's gravity keep most of its outer layers from leaving. However, some of the gas is moving fast enough, around 1 million kilometers per hour, to escape the sun's gravity forever and race into space. A portion of this gas comes directly from the corona with the help of the sun's magnetic fields, while some of it is funneled out from below the corona, also by magnetic fields. The outflow of particles is called a solar wind. Just as the sun has a solar wind streaming out past the planets, other stars eject analogous stellar winds of varying intensities, some weaker than the solar wind and others much more intense. Therefore, flows of particles from other stars called stellar winds approach the solar wind from all directions. At a distance of approximately 115 AU from the sun, the two flows collide. Combined with the magnetic field of the sun, discussed further in section 11.5, the solar wind prevents most of these stellar wind particles from entering the inner solar system, thereby creating a heliosphere. The boundary of the heliosphere, called the heliopause, is lopsided because the solar wind is orbiting in the Milky Way galaxy, and therefore is plowing through the solar winds created by other stars. The interaction between the solar winds and the direction we are moving and the stellar winds creates a tail of solar wind particles in the opposite direction of our motion through the Milky Way. Astronomers think that the sun's chemical composition today is nearly identical to the composition of the solar nebula from which it formed. Although electrons and hydrogen and helium nuclei comprise 99.9% of the solar wind, silicon, sulfur, calcium, chromium, nickel, neon, and argon ions have also been detected in it. Granules, supergranules, spicules, and the solar wind occur continuously, but the sun's atmosphere is also periodically disrupted by magnetic fields that stir things up, creating a group of phenomena collectively known as the active sun. The sun's most obvious transient features are sunspots, regions of the photosphere that appear dark because they are cooler than the rest of the sun's lower atmosphere. Sometimes sunspots occur in isolations, but often they arrive in clusters called sunspot groups. There's also a sunspot cycle which repeats every 11 years, where every 11 years you have a peak in the number of sunspots, and halfway through you get a minimal amount before going back up to the peak, as seen in the diagram and the pictures in this slide. By following sunspots as they moved around the solar disk, Galileo discovered that the sun rotates once in about 4 weeks. He did this by observing the sun directly or indirectly, using the technique developed by his protege Benedetto Castelli of projecting the telescope image of the sun on a screen. Because a typical sunspot group lasts about 2 months, it can be followed for 2 solar rotations. Sunspot activity also reveals that, like latitudes, different latitudes of the sun rotate at different rates, a phenomenon called differential rotation. The equatorial regions rotate more rapidly than the polar regions. A sunspot near the solar equator takes 25 days to go, whereas one near the pole takes as long as 35 days. Sunspots are areas where concentrated north and south magnetic fields project through the hot gases of the photosphere. But how do these fields create the spots? The answer lies in the interaction between the magnetic fields and the solar photosphere's gases. Because the photosphere's high temperature, many atoms in it are ionized. As a result, the gases of the photosphere are plasma. Plasmas are extremely good conductors of electricity and are repelled from regions of high magnetic field. Therefore, the magnetic field protruding through the photosphere prevents hot ionized gases inside the sun from convecting to the surface in the form of granules, as they normally do. Thus, regions in the photosphere through which magnetic fields pass are left relatively devoid of hot gas, and we therefore see cooler and darker than the surrounding granule-rich solar surface. We see these darker, cooler regions as sunspots. To learn more about the sun's interior, astronomers record its vibrations, a study called helioseismology, just as geologists use earthquakes to study Earth's interior surfaces. Although there are no true earthquakes, the sun does vibrate in a variety of ways, somewhat like a vibrating drumhead, which, when struck at different places, makes different sounds due to different modes of vibration. Solar vibrations, first noted in 1960, can be detected using sensitive Doppler shift measurements. Astronomers have observed, for example, that portions of the sun's surface move up and down by about 10 kilometers every 5 minutes. Slower vibrations, with periods ranging from 20 minutes to nearly an hour, were discovered in the 1970s. Oscillations lasting several days have been detected, as have pulses 16 months long. One important discovery from helioseismology is that deep inside, the sun rotates like a rigid body, rather than the differential rotation we see on its surface. While observing the vibrations of the sun around sunspots, astronomers in 2001 apparently found the answer to the question of how sunspots persist for months despite the repulsion of the magnetic fields inside them. They discovered that below the photosphere, the gases surrounding each sunspot whip around like hurricanes as large as Earth's diameter. The circulation of charged gases around the magnetic fields holds sunspots in place. During his observations, Hale found that on one hemisphere of the sun, sunspots with a magnetic field North Pole always come into the view before the corresponding sunspots with a magnetic South Pole. At the same time, on the other hemisphere, the order is reversed. Hale also found that this pattern reverses itself about every 11 years. The hemisphere where north magnetic poles come first during one 11-year cycle has south magnetic poles coming first during the next. Astronomers therefore speak of the 22-year solar cycle, or 11 times 2 years of a solar cycle, the time it takes for solar magnetic fields to return to their original orientation. This shows the active sun's chromosphere and corona. The bright areas in the photograph are called pulsars. By studying the light emitted by calcium or hydrogen atoms in the pulsars, we know that they are hotter and therefore brighter than the surrounding chromosphere. Pulsars, which often appear just before nearby sunspots form, are thought to be created by the magnetic fields under the photosphere crowding upwards just before they emerge through the photosphere. In pushing upwards, the fields compress the gases in the upper sun, causing this gas to become hotter and therefore to glow more brightly. The dark streaks in 1115, this diagram, are called in the corona called filaments. These features are huge volumes of gas lifted upward when the photosphere by the sun's magnetic field. When viewed from the side rather than from above, filaments form giant loops or arches called prominences. The temperature of the gas's prominence can reach 50,000 Kelvin. These features almost always associate with sunspots. Some prominences last for only a few hours, whereas others persist for months. The gases in the most energetic prominences escape the magnetic fields that confine them and surge out into space. X-ray photographs also reveal numerous coronal bright and dark spots that are hotter or colder, respectively, than the surrounding corona. Temperatures in the bright regions occasionally reach 4 million Kelvin. Many of the bright coronal hotspots are located over sunspots. The darker, cooler coronal holes act as conduits for high-speed jets of gases to flow out of the sun. Therefore, when a coronal hole on the rotating sun faces Earth, the solar wind in our direction increases dramatically. Violent eruptive events on the sun were first observed in 1859. These solar flares release vast quantities of high-energy particles as well as X-ray and ultraviolet radiation. Solar flares sometimes occur when sunspots collide. Typical flares each emit as much energy as is contained in all the fossil fuel ever contained inside Earth. Flares are so powerful that they leave the region of the surface of the sun in their vicinity, quaking for an hour or more. At the maximum of the sunspot cycle, about 1,100 flares occur per year. Most of them last for less than an hour, but during that time, temperatures in the sun's corona soar to 5 million Kelvin. By following the paths of particles emitted by flares as they are deflected by the sun's magnetic field, astronomers have since the 1960s been mapping that field as it extends out beyond Earth. Astronomers have also observed huge balloon-shaped volumes of high-energy gas being ejected from the corona. These coronal mass ejections expel up to 10 billion tons of matter at once, and each one lasts for up to a few hours. Some coronal mass ejections occur when the sun's magnetic field violently changes its shape, therefore releasing large quantities of gas that had been trapped in it. Other coronal mass ejections are caused by tornadoes of extremely hot gas that originate in the photosphere, rise, become unstable, and then violently inject large volumes of gas. Solar flares have also been observed to create shockwaves that initiate some coronal mass ejections. The origins of other ejections are still under investigation. The number of prominences, flares, and coronal mass ejections vary with the same 11-year cycle as the number of sunspots. However, coronal mass ejections, the major source of hazardous particles from the sun, never completely cease. Some coronal mass ejection solar flares and filaments head toward Earth. Their electromagnetic radiation gets here in about 8 minutes. Their high-energy particles arrive a few days later. At times when these surges of particles are not coming towards us, the normal solar wind particles are trapped by Earth's magnetic field in the regions called the Van Allen belts. The additional particles form a coronal mass ejection or other solar event that do come our way overwhelm the Van Allen belts, enabling matter in them to cascade earthwards. One of the most spectacular of such events in recent years occurred around October 31st, 2003, filling the night skies with aurorae in many places around the world. Strong surges or high-energy particles from the sun-damaged satellites disrupt radio communications, short out power grids here, produce intense aurorae in Earth's atmosphere, cause some of Earth's atmosphere to gush into interplanetary space, and potentially harm or kill people in space. Collectively, the activity from the sun that can affect us is called space weather. Much of the physics of the sun comes from the equation E equals mc squared. In other words, mass m can be converted into the amount of energy E equivalent to E equals mc squared, where c is the speed of light. Namely, c squared is 9 times 10 to the 10th kilometers squared per second squared. A small amount of matter can be converted into an awesome amount of energy. Inspired by Einstein's work with this equation, physicists discovered that the sun's energy output comes from the conversion of matter into energy. In the 1920s, the British astrophysicist Arthur Eddington proposed that the temperature be at the center of the sun, its core, is much greater than had ever been imagined. Calculations eventually revealed that the temperature there is about 15.5 times 10 to the 6 Kelvin, or 15 million Kelvin. Physicists also showed that the temperatures above 10 times 10 to the 6, or 10 million Kelvin, about hydrogen fuses into the element helium. In each such reaction, a tiny amount of mass is converted into energy in the form of gamma rays. Enough fusion occurs in its core to account for all of the energy emitted by the sun. A scientific theory describing the sun's interior, called the solar model, explains the interior features of the sun and how the energy from nuclear fission or fusion at its core gets to its photosphere. The model begins with the inward force that the sun's mass creates as a result of its gravity. The force compressing the matter in the core increases the pressure and temperature there, which, as we just saw, causes hydrogen fusion to occur. Because the sun is not shrinking today, however, there must be an outward force through its interior that counters the inward force of gravity. That outward force is caused by the gamma ray photons generated during fusion. The outward movement of energy by photons hitting particles, which then bounce off other particles and thereby re-emit photons, is called radiative transport. Because individual photons are responsible for carrying energy from collision to collision, calculations show that radiation transport is the dominant means of outward energy flow in the sun's radiative zone, extending from the core to about 70% of the way out to the photosphere. Near the photosphere, energy is carried by the remaining distance to the surface by the bulk motion of the hot gas rather than the flying energetic photons. The circulation of gas blobs is called convection. We thus say that the sun has a convective zone. Hot gas travels to the top of the zone by convection, and from there it radiates photons into space. These photons are what we see as sunlight, and you can see that the photosphere, which is at the bottom of the solar atmosphere, is also at the top of the convective zone. From fusion to sunlight usually taking about 170,000 years. Once the gases in the convective zone lose energy by emitting photons into space, they cool and settle back down into the sun. As noted earlier, this convective flow is also the origin of solar granules, and the departing energy is the visible light and other electromagnetic radiation that the sun emits into space. Here we see various quantities as you go from the center of the sun to the surface of the sun, and you will see that luminosity goes towards it's 100% very close to the surface of the sun, about 0.2 of the or 20% of the way towards the surface of the sun, while mass is basically at the 100% as you go towards about halfway towards the surface of the sun. And the temperature goes from 16 times 10 to the 6 Kelvin to basically 10 to the 4th Kelvin as you get around 0.7 or 70% of the way to the surface of the sun, and the density goes basically to very low density, very small density compared to the center of the sun, about 0.4 or 40% of the way through the surface of the sun. When the sun was young, the larger number of hydrogen atoms, that is, the larger number of isolated protons in its core, created more repulsion than the core experiences today. With its larger number of neutron-rich helium atoms, each containing 2 protons held together by 1 or 2 neutrons, the greater repulsion in the younger core prevented it from heating up as much as the denser core of today. Therefore, the young sun with its cooler core had less fusion occurring because the cooler a star's core is, the lower the rate of fusion it experiences. Using the equations of stellar structure on the younger sun with its cooler core reveals that the gamma rays created by the fusion back then did not push the outer layers out as much as they do today. Hence, the sun was smaller, but the equations also reveal that the surface of the smaller, younger sun was about the same temperature as it was today. Because it had less surface from which to radiate, the young surface emitted less energy than it does today. It was dimmer. The fact that the sun was cool when the Earth first formed raises the question of whether the sun always provided enough heat to allow water to be liquid on Earth's surface. There's overwhelming geological evidence for liquid water back at least 4.2 billion years ago. However, if everything on the Earth was then as it was today, the young sun did not heat Earth sufficiently for its surface water to be liquid. Geologists are still trying to explain how Earth was able to have liquid water on its surfaces at a time when the sun was not heating our planet sufficiently. This is called the faint young sun paradox. The paradox may have been resolved by noting, as we discussed earlier, that the greenhouse effect created by the Earth's early CO2 atmosphere may have kept the Earth sufficiently warm so that the water was liquid even back then.